All right, this is about binary dependent variable. Y is binary. It takes 1 or 0, so that is the binary case. So it is pretty simple. We only care about the probability of 1. Then automatically probability of failure is 1 minus that probability. And here f is the link function. And so what is interesting here is xi is k-dimensional information. And we are going to summarize this to xi transpose beta 0, which is one dimension. And then f only sends just one dimensional information to one dimension, like it's a probability, so between 0 and 1, right? This is what it does. So this is called index. So in econometrics, we call this index model, and in statistics, we call this link function. So even if there are many observations, many dimensions, still we summarize them first by linear model, and then we send it to a nonlinear link function, right? Let's think about it. So probability, we only have two probabilities, probability y equals to 1 or y equals to 0. When y equals to 1, it is f x transpose beta, and when it is 0, it is 1 minus f transpose beta. Okay, pretty simple. And mathematically, the simplest way to express this is probability y equals to t given xi is f xi transpose beta 0 to the exponent of t. Let me keep doing this. Transpose beta 0 to the exponent of 1 minus t. So if t is 1, then this is 1, this is 0. So the probability becomes, so something to the exponent of 0 becomes 1. So, and something to the exponent of 1 is itself, right? Times 1, which does not matter, right? That is the probability, okay? That is exactly what we want. And if t was 0, then now this part becomes 1 because the exponent is 0, and this becomes 1, so the probability becomes 1 times 1 minus f, this guy. So again, that's what we want. So this is part A. And let's calculate the log likelihood function. Log likelihood is log of the probability. But your probability must depend on the observed y. So if y is 1, then you plug in this. Y is 0, then you plug in this. But at the same time, we can utilize this one. That means yi times log of fxi transpose beta 0 plus 1 minus yi log of fx, 1 minus fxi transpose beta 0. That here this is a function of beta. So Li beta will be defined as yi log fx transpose beta plus 1 minus y log fx transpose beta. Okay, this is the log likelihood function that we are going to maximize, right? So we have done this and this. And we are going to do the calculus, right? So like before doing the calculus, let's think about it. So remember, f is r to r, real to real function. So I'm going to define g, which is also one dimension to one dimension, as the derivative of t, like say t for temporary. So ft differentiated with respect to t. So it's one dimensional differentiation. So for example, if you differentiate this, then we are going to differentiate this way, chain rule. Right? So this is how we are going to differentiate, and this part will be denoted as g. And the second derivative will be denoted as h, right? This is second derivative, right? Anyhow, then back to the log likelihood. It's a little complicated. Log f xi transpose beta plus 1 minus y log 1 minus f x transpose beta. Here, I'm going to differentiate. Then it becomes, here first, if you differentiate with respect to log, then you get this first. And then differentiate inside log, then you will get x times g of xi transpose beta. Right? Right? As you remember, this becomes x, this becomes g. Plus, similarly, you are going to, but here is a negative sign, so I will use negative sign here, but everything else is the same. xi g xi transpose beta times 1 minus y over 1 minus f x transpose beta. That is the first order derivative. Second order derivative, it's even more annoying, is first, if you differentiate with respect to g, then you will get let me just simplify it to f, right? So this is when you differentiate with respect to this beta here and here, right? And factor out these guys. And then also you have to differentiate with respect to here and here. That will become minus xi transpose gi squared, actually it's one dimension, gi squared times yi over fi squared. Let me simplify like this. And if you differentiate with respect to the last term, then it becomes minus xi transpose gi squared times 1 minus y over 1 minus f squared. I think this is right. Okay, so then let's factor out these guys. So xi transpose, and then hi yi over fi minus 1 over 1 minus y, 1 minus f. This is up to here. And then second term minus gi squared times yi over fi squared minus plus 1 minus yi 1 minus fi squared. This is the second order derivative. Okay, the next question is, so we just did it. And let's see, the first order condition is satisfied. The first order condition is from here. So let me rewrite the first order condition. Is xi g xi transpose beta times yi over f xi transpose beta minus 1 minus y 1 minus f beta transpose. Okay, and we are calculating its expectation at beta 0. Expectation at beta 0 equals, so this guy, so expectation of xi, let me write it as just gi, times, excuse me, yi over fi, simply, minus 1 minus y over 1 minus fi. We are going to use law of iterated expectations as usual. So everything that does not depend, that depends only on xi will come out of the expectation like this. So expectation of yi given x over fi minus expectation 1 minus I given x over 1 minus fi, right? And then remember it is binary, so expectation of y given x equals probability of y equals to 1 given x. This is the basic property for any binary random variable. That means this is f and this is 1 minus f, right? So it will be cancelled out by like become 1 and also become 1. So 1 minus 1, so it will be 0. Okay? So the point is low iterated expectation is the main form. And then the next question, we just did it. And then we are going to show the second order derivative is non-singular. Oh, yeah, it's so annoying. Second derivative is x transpose, up to here no problem, and then hi, let me go peek again, okay, y over f minus 1 minus y over 1 minus f plus or minus gi squared yi over fi squared plus 1 minus y and 1 minus f squared. This is the second derivative, and its expectation at beta 0 is, so again we are going to use the law of iterated expectations. So first I will just write this first, and then here comes the conditional expectation minus 1 minus expectation yi given xi 1 minus fi. Okay, this is the first term, and we know they cancel out, so the first term is gone. And then minus gi squared and expectation y given x over f squared plus 1 minus expectation y given x over 1 minus f squared. Okay, so this term does not go away, but still it is f, right? Numerator is f, so square is gone, and this is 1 minus f, also square is gone. So we can simplify minus expectation of gi squared times 1 over f plus 1 over 1 minus f. Okay, pretty simple, and it can be even simplified to gi squared and here it becomes fi times 1 minus fi as a whole term. You can just factor out that. That's simple. And now we have to show that it is non-singular, right? So first, let's go back to the assumption. So f is strictly increasing, so thus g is strictly positive. So g is not 0. That part is clear. G is, it's a scalar. It's not 0. And also, we are assuming that f, the probability is strictly greater than delta and strictly smaller than 1, right? So that means by the way, where is x prime x? Oh, I forgot to say. Sorry, so I missed it. xi prime, xx prime. Sorry about that. And so I just argued that g is strictly positive, and these are also positive, like not 0, right? So f is greater than 0, and 1 minus f is also greater than 0. So as a whole, these guys are always also greater than 0, strictly positive, okay? And then finally, you are going to get expectation xi transpose times something strictly positive. This is like if x prime is and then we also have this assumption, right? Already expectation of x prime is non-singular, then a new expectation after multiplying a positive thing is still non-singular. Okay, I will continue in the next video.